go ahead and get started.
Yeah.
So in fact, so today what I want to do is I want to talk about flat and moduli spaces of flat and hyperbolic structures on surfaces. Actually, let me see if I can hide this. Sorry. Okay. So this doesn't need. There we go. Hold on. Sorry. Let me try this again. I think I lost my screen sharing. Yeah, that's fine. Okay, that's better. And let me just hide this. Oof, sorry. Just having some trouble with my screen sharing. There we go. Okay, so I don't, yeah, there's this little thing at the bottom which I'm trying to get rid of. Unfortunately, that doesn't seem to go away. But okay, so I'm going to tell you about flat moduli spaces of flat and hyperbolic structures on surfaces. So last time we looked at sort of the moduli space of triangles, and we looked at the moduli space of flat tori. And today our goal will be to look at moduli spaces of flat structures on higher genus surfaces and moduli spaces of hyperbolic structures on higher genus surfaces. And intermediate, we'll also have to talk a little bit about moduli spaces of complex structures. So we have flat structures, hyperbolic structures, and complex structures. So let's get started with an example. So last time we started to talk about, we talked about, if we go back to tori, we said, oh, we took a square and we identified opposite sides, or we took a parallelogram and we identified opposite sides, or we took some maybe long, skinny parallelogram and identified opposite sides. And these were all examples of a flat torus, just coming from different geometries. And so what we would like to do is we'd like to generalize this picture to kind of a higher genus surface. And so one way to do that is, so this was a genus one surface, genus, or the number of holes, and that was, we did it with the 4G gon, right? So this is a 4 gon. So maybe what we should do is we should say G equals 2. So we want to look at sort of surfaces that have 2 holes, and we want to associate this to an 8 gon. Maybe we should, let's see, can we make a genus 2 surface out of something with 8 sides? And the answer is yes. In what sense are the geometries are different in the tori? Well, in the sense that, for this one, if you look, for instance, at these, this one has, let's say, these 2 curves, let's say a pink curve and a yellow curve. The yellow curve and the pink curve on the square have the same length, right? And in this one, for instance, if you look at this far one over here, this yellow curve and this pink curve, maybe the yellow curve is very, very long compared to the pink curve. So in that sense, they have different geometries, right? So one looks much more kind of square and round. Sorry, this keeps happening. I don't know how to, hold on one second. I just want to, let me see if I can get this to disappear here. Okay, so let's do that. And then let's go here. Okay, I guess I can't get, unfortunately, I cannot get that thing to disappear, this thing at the bottom of the screen. But their geometry is different in the sense that the aspect ratios are different. So here, you'd have this very long yellow curve and this very short pink curve. So does that make sense? Does that answer the question?
Yeah. It's good. Yeah.
Great. So
We can
again,
just.
similarly here, we're going to want to try and build octagons, and we're going to try and build genus 2 surfaces out of octagons, and we would like them to try and understand the different geometry. So first I want to say, how do we build a genus 2 surface of an octagon? So let's take a very concrete example of an octagon. Let's just take a regular octagon. This is supposed to be a picture of a regular octagon. Okay, so it has 8 vertices, 8 sides. What I'm going to do is I'm going to identify the opposite sides. So maybe this side is identified to this side, this to this, this to this, and this is the fourth side, and this is the fourth side. I could also use some colors. So maybe let's use some colors. Maybe this side is yellow, and maybe this side is pink here. And then maybe this side is green, and this side is blue. And now what I'm going to do is first I'm going to make a very bad joke. I'm going to say, well, why don't we complete the square? Why don't we make this into a square? So what I'm going to do is I'm going to extend the yellow side, and then I'm going to extend the pink side. And I'm going to think of this as a big square. And if I identify opposite sides of a big square, of course, I get a torus. And so this torus here, and I'll draw this in a second, has this one. Oh, I'm sorry. This one big yellow sort of curve going around it, and this other pink curve going around it. And except where they meet, around where they meet, we have this little green and blue which is not really part of our surface, right? That's not really part of our surface. So maybe I should kind of shade this in white, right? This is not part of our surface because we only want to consider the octagon. So I have this kind of hole in my surface, this square hole in my surface, and what I'm doing is I'm gluing opposite sides of this square hole. And so when I glue the opposite sides of the square hole, I pick up some more genus, and I get this genus 2 surface, where let's see what's happened to this point, this corner. So here, if I'm identifying opposite sides of this green and this blue, all those 4 corners collapse to 1 point. And that's really, you can also see it from this original picture. You can see this is, it's the right side of pink, so it's here. It's this side of green, so it's here. It's the top of yellow, so it's here. It's this bottom right of blue, so it's here. It's the left of pink, so it's here. It's the top right of green, so it's here. And it's the bottom of yellow. So all the 8 corners collapse to 1 point. The interior angle of an octagon is 3 pi over 4. You can also see here all of these angles. The interior angle is 3 pi over 2. So you get this 1 point with angle 6 pi. This is something new. When we did the torus, we only had, we would glue opposite sides of the square. And when we glued opposite sides of the square, we got this, when we glued opposite sides of the square, sorry, we had, let's see if I can reorient this a little bit. 90 plus 90 plus 90 plus 90, this point had just an angle of 2 pi, right? So this was pi over 2. And we had, when we added them up, we got this, this 2 pi. But here we actually get a point with angle 6 pi. By the way, can everyone still hear me? It looks like, is my video frozen? Is my audio audible to you?
No, everything is fine. Everything is fine.
Everything's fine. Great,
Yeah.
great.
Yeah.
Okay, so now, so what we see is that gluing opposite sides of the Euclidean octagon yields a genus 2 surface with one singular point with angle 6 pi. So it's singular because that point looks genuinely different from every other point. So here's an exercise that is, I think, really nice. And it's an excellent exercise in general. Exercise, show that gluing, so this is maybe exercise part 1, opposite sides of a regular 4G-gon yields a genus G surface with one singular point of angle, it's going to be 2 pi times 2G minus 1. Okay. So notice if G is equal to 1, you get an angle 2 pi. If G is equal to 2, you get an angle 6 pi. You might say, well, why did you go from a square to an octagon? Why did you skip the hexagon? So exactly the same exercise, but if you did a 4G plus 2 gon, then you get 2 singular points with angle 2 pi times G. Let's see, write this like this. Each of them has angle 2 pi times, not G minus 2, excuse me. So it's 2G minus 2, 2 pi times G minus 1. Yeah, 2 pi times G minus 1, exactly. Okay. And so let's actually just see this quickly for the hexagon. Let's see what happens with the hexagon, just because I didn't mention it last time. So until now, so if we have the hexagon, so this is a 6-gon, and we identify opposite sides. Let's see what happens to this corner point. This corner point, that's the right side of 1, so it's glued to there. It's the bottom left of 3, so it's glued to there. And now we come back to where we started, and if you notice, the angle here is just 2 pi over 3, the interior angle of a hexagon. And similarly, we could take this point, and this point is glued, well, first to this point, then to this point, and this also has angle 2 pi over 3, 2 pi over 3, 2 pi over 3. So when you glue this, you end up getting a torus, and you have these 2 special points. You have a pink point and a blue point, but they both have angle 2 pi. So they're not really singular points. They're very nice points, but more generally, you can generalize this picture to a 4G plus 2 gon. And if you remember, actually, just going back, this torus is the one that sits here. This is the hexagonal torus that we talked about here, and this one is the square torus that we talked about here. Right? So this is back to the connection to lecture 1. But if I have these, as soon as G is, so notice, for G bigger than 1, we have points with angle bigger than 2 pi. So i.e., this is saying something is that the geometry has gotten a little strange. Has gotten strange. And the reason that the geometry has gotten strange, of course, is the classical Gauss-Bonnet theorem, which says that if you integrate the curvature over the surface, right? So if you integrate the curvature over the surface, if you integrate curvature over the surface, you get the Euler characteristic, right? You get or minus the Euler characteristic of the surface. And there's a pi involved here. So there's a 2 pi here. And so as soon as genus G is bigger than 1, we have the Euler character, we get the Euler characteristic, As soon as my genus is bigger than 1, the Euler characteristic of my surface of genus G is negative, right? This is 2 minus 2G. And so I have to have my surface has to have negative curvature. So the geometry of the surface should have negative curvature. And of course, by trying to make it flat, by trying to take a Euclidean polygon and glue opposite sides, I've been having sort of flat curvature. And so that means I'm going to have some places where I have problems. And basically what I'm doing when I take a flat polygon and glue opposite sides, so taking a Euclidean polygon yields a singular flat metric. And in some sense, what we've done is we've put all the curvature at a finite set of points. So when we have all the curvature at a finite set of points, the natural question is, what would the, in some sense, right geometry be? i.e., is there a constant curvature geometry without singular points? And the answer, of course, as you guys have learned in your introductory lectures, is yes. And that answer is the correct geometry in some sense for these surfaces is hyperbolic geometry. Okay, so what do I mean that the correct geometry is hyperbolic geometry? Well, let me draw you a kind of picture here. So let's take the disk and let's think of the hyperbolic metric on the disk. Let's think of the disk as so of course you can think of this as a model of hyperbolic geometry. You can also think conformally this is the same thing as the upper half plane. And in the upper half plane, the metric is of course just bz squared, I'm going to write this over y squared here, but really it's, you take this, so, well, let me just write it like this. It's square root of dx squared plus dy squared over y, that's ds, right? And here you can also write what the hyperbolic metric is. But again, if you don't remember any of that, the key point is the geodesics here are semicircles or circles orthogonal to the boundary. So geodesics in this metric, shortest paths equal circles sort of perpendicular to the boundary. So let me draw you an octagon here. First, I'm going to draw you a very careful octagon on this. Let me just draw you some 8 equally spaced points here. So maybe 1, 2, 3, 4, 5, 6, 7, 8. And I'm going to draw you a kind of a bunch of hyperbolic geodesics. So all of these are going to be hyperbolic geodesics. All of these angles are pi over 2 here. And all of these angles are just 0, right? So these are all having angles of 0. And this is supposed to be just the center of this thing. And if I glued opposite sides of this sort of hyperbolic octagon, this is a very special hyperbolic octagon. This is not the standard gluing that you see actually when you do this, but that's okay, because you can still make this work. If you were to identify sort of opposite sides using hyperbolic isometries, you would get actually here, in this case, a genus 2 surface with a puncture. And the puncture would exactly correspond to this boundary point at infinity. And there would be sort of a zero angle at this point. So this would be a punctured hyperbolic surface. But now suppose you moved you just started to slide these vertices in along these radial straight lines. And you started to look at the geodesics like this. You started to look at these smaller hyperbolic octagons. And then as your hyperbolic octagon gets smaller and smaller and smaller, as you zoom in, it's starting to look more and more like a Euclidean octagon, right? You zoom in, it's starting to look more and more like a Euclidean octagon. So you can interpolate between a Euclidean octagon, which is kind of what you get in the limit here, which has angles, the interior angle is 3 pi over 4, and here, where the interior angle is just 0, and in between, there will be something where the interior angle is actually pi over 2. And now, when you identify opposite sides of that, you get a genus 2 surface, and that all those 8 corners collapse to 1 point, and when you have 8 times pi over 2, pi over 4, excuse me, is what I want, and you get this point here, which will have angle exactly 2 pi, right? So the key point here is that by interpolating between what's called an ideal hyperbolic octagon, i.e., all vertices on the boundary, all angles 0, and a Euclidean octagon, all angles 3 pi over 4, you can find a hyperbolic octagon with all angles equal to pi over 4. Right, this is just kind of by the intermediate value theorem. And this gives you a genus 2 hyperbolic surface that is a constant curvature surface with no singular points whatsoever. Everything looks extremely nice. No singular points. But you might ask, I said at the beginning of this series that I was going to tell you about a space of such things. I've just demonstrated one of these things for you that I've started, say, with a regular Euclidean octagon, and I've showed you how to build kind of a hyperbolic octagon. But are there more? Is there kind of only one way to build a hyperbolic genus 2 surface, or is there more? Are there more ways of doing it? And here, it's again kind of useful to go back. It's really useful to go back to kind of the flat picture and go back between the flat and the complex picture. So let me actually say a little bit of words about the complex structures that are hiding here. And then we're going to quote this massive and beautiful theorem of Poincaré, the uniformization theorem, which will tell us that in fact, you can go between flat geometry and hyperbolic geometry in a really interesting way. So let me first say, so the upshot is there will be many hyperbolic genus 2 surfaces. In fact, the dimension of the space will be 6. It will be a 6-dimensional space. More generally, if you look at the dimension of what mg, which is the moduli space of genus G surfaces, this has dimension 6g minus 6. This is for g bigger than or equal to 2. Excuse me, sorry. Whoa. And I'm going to show you a little bit. So one way to see this is via what are called Fenchel-Nielsen coordinates. And I'll talk a little bit about this in a minute, Fenchel-Nielsen coordinates. But I also want to talk about the uniformization theorem. I'm not going to try and prove it. That would take a whole semester, but I want to at least try and show you how it shows up in this situation. So we start with, so maybe I'll start with an observation. There are many singular flat geometries on genus 2 surfaces. So for instance, I drew you that regular octagon, but I want to draw you another thing that may not look so much like an octagon, but it still is. Let's draw this kind of L shape. And I'm going to mark a few points here. I'm going to mark this point and this point and this point. And I'm going to make some identifications. So maybe this yellow side is glued to this yellow side. Maybe this side is glued to the pink side. This blue is glued to this. And maybe this green, sorry, that's the blue again. This green is glued to this green. And again, very similarly, if I glue these opposite sides, I could glue the opposite sides, the yellow and the kind of the pink. And again, I would sort of complete the square and I would get another hole and I would get this genus 2. And now what you see here is you again see this is the top of yellow, so it's glued to this. It's the right of blue, so it's glued to this. It's the bottom of yellow, so it's glued to this. It's the left of pink, so it's glued to this. It's the top of green, so it's glued to this. And it's the right of pink, so it's glued to this. And it's the left of blue, so it's glued to this. So all 8 collapse to 1 point. You have angle 3 pi over 2 plus 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 pi over 2. And so you get this, again, you get this point with the total angle of 6 pi. And again, it's where sort of this, you have these closed curves, which are blue and green respectively intersecting. And then again, also these yellow and these, you have all these 4 closed curves kind of intersecting. So you could think of, I have this yellow curve and I have this pink curve and I have this green curve and I have this blue curve, all intersecting, and they're all making an angle of sort of pi over 2. Okay, so let me, this is another example. And of course, notice now I could just change the lengths of the yellow and the pink and the blue and the green, and that would give me kind of different geometries. I could also kind of tilt things a little bit or skew things, right? I could do something like this and do a very similar gluing process, right? And so really, I have a lot of freedom over what I can do to make a genus 2 flat surface. So there's a lot of freedom. In fact, you can say, well, what I really need is I just need sort of 4 vectors in R2, kind of I'll have R2 to the power 4. And maybe if I care about things only up to scaling, maybe I quotient out by sort of acting by, if I just scale the whole picture by a positive real number, that's not so exciting. So maybe I just sort of, this is sort of a 7-dimensional space. So already this is kind of a very large space of flat surfaces. I can just tweak things, and this is I can do a lot there. And then we have this amazing theorem. So also, by the way, notice before I state uniformization, any flat surfaces gives me a complex structure on my surface. Why? Well, simply because translations are holomorphic maps. Notice I'm gluing everything here by translation. I'm taking the surface, I'm taking this domain in C, so thinking of this as sitting inside of C, and I'm gluing everything using translations. So whenever I have one of these, I actually have a complex structure on the surface. I have locally, everything just looks like C, and the transition maps between any transition maps are just translations which are holomorphic, so I have a complex structure. And then I have this massive hammer of the uniformization theorem, which tells me for every Riemann surface, every complex structure, X, there exists a unique constant curvature metric in the conformal class of X. That is where angles are kind of the same, conformal class of X. And for if genus is bigger than 1, that is a hyperbolic metric. Right, so this theorem goes back to Poincaré and is one of the foundational theorems of hyperbolic geometry. For instance, if you go back to a complex analysis class, this theorem is very difficult, but another theorem that's kind of relevant to this is, say, right, which tells you what the right thing to do to get the complex structure on, say, a thrice punctured sphere is. Okay, let me just black box the uniformization theorem for a minute. But the whole point is, so many flat structures lead to many complex structures, which lead to many different hyperbolic structures. Okay, but I also promise you that I promise at least kind of information why the dimension of the space of, maybe I'll just say why this dimension, for instance. So mg here is the space up to isometry, the space of genus G hyperbolic surfaces up to isometry. And this should be not 3, but 6. And more generally, I want to give you intuition about why the dimension of the moduli space of genus G surfaces is 6G minus 6. So let's go back to the genus 2 example, and let's say I have a genus 2 surface. And I have some hyperbolic structure on it. So this is some point inside of MG. And so what I'm going to do is I'm going to fix what's called a Pantz decomposition of the surface. In fact, I'm going to cut the surface along these 3 curves. If I cut the surface along these 3 curves, and maybe actually I should color them differently. Maybe I'll color this guy pink, and I'll color this guy green. Okay. So these 3 things. Now what happens? If I cut the surface in 2, I now have this, and I have this, and I have kind of 3 boundary components on each of these. I have this guy here, I have this guy here, I have this guy in the middle here, and then of course I have some sort of connecting tissue here. So I have these 2 things that look like, well, they're called pairs of pants because a pair of trousers has 3 holes, right? So you have the waist, and then you have the 2 legs. But you could also think of this as, for instance, if you have some sort of pipe with 3 holes. And I need to be able to, I want to just glue these things together. Now, each of these is a sphere with 3 boundary components. Sphere with 3 boundary components. Both of these are spheres with 3 boundary components. Apologies, my handwriting is getting a little bit bad. So now the question is, so there's a couple of points. One, again, we're going to black box the following thing. The hyperbolic structure on a sphere with 3 boundary components is completely determined by the length of the boundary components, the lengths of the boundary. So as soon as I know the lengths of these boundary components, I know the full details of the hyperbolic metric on each piece. So that's already sort of 3 numbers here. So I have an L1, maybe an L2, and an L3, and of course they have to be the same on either side. So these are 2 copies of the identical hyperbolic sphere, spheres with 3 boundary components. And now what I need to do is I need to tell you how to glue them together. And now, if you have 2 circles and you want to kind of glue them together, you can glue them together, well, you can twist, right? You can kind of think about how much threading you want to do if you think about, say, a screw. So to each thing, I also have a twist parameter, which is sort of in between 0 and the length, right? So I have a twist parameter, which is in between the length and 0. So it's telling you sort of how much I can twist this. So these are what are called, these numbers are called, the set of parameters sort of Li tau I equals 1, 2, 3, are called Fenchel-Nielsen coordinates. And there are, for this genus 2 surface, notice there's 6 of them. And so this is telling you exactly that dimension of R of M2 is 6, that you have 6 of these 6 numbers, and they completely tell you how to move around once you fix what's this thing called a Pants decomposition. More generally, if you take a genus G surface, for a genus G surface, you need 3G minus 3 curves in what's called a Pants decomposition. That is, you need 3G minus 3 curves to cut the surface up into spheres with 3 boundary components. And so what you get as coordinates there, once you fix the Pants decomposition, is Li tau I equals 1 to 3G minus 3, which will give you your dimension. Now, I haven't proved anything. I've just given you a very impressionistic idea of why there's kind of, this is the right size for this moduli space of hyperbolic surfaces. Now, I said I would also tell you about a relationship between the space of flat surfaces and the space of hyperbolic surfaces. Why is tau great? Thank you for this question, Professor Tabati. The idea is, I have these 2 things of length, of a fixed length. I can't twist more than the length, right? Let's identify a point on each side. I could either just, I could glue them, that would be sort of 0, or I could just think of how much I'm moving one relative to the other, right? All motion is happening relative to Li. So I could choose tau I to be in any range of, say, size L, but I'm just going to choose it to be between 0 and Li. This is the difference between, by the way, this is a subtle point maybe for the experts, between moduli space and Teichmuller space. In Teichmuller space, I do allow the twist to be as big as I want, but in moduli space, I allow the twist only to be between 0 and Li, because I can always deign twist so that the twist comes back between 0 and L. Thank you. That's an excellent clarification. Okay, so what's, why do I want to talk about these flat structures and these hyperbolic structures at the same time? Well, there's a really interesting relationship between the geometry of the space of hyperbolic structures, the space of complex structures, and the space of flat structures. And I want to just hint at this. This is a classical piece of work by, it goes back to Teichmuller, and then the other names that we should mention here are really Alfors and Bears. But here's the key point here. So connection, or this is just one connection between sort of the flat and hyperbolic geometry. And it's going to go in between, we're going to use the complex geometry and the complex analysis. So let's say I have a Riemann surface X is a Riemann surface of genus G, and Y is a different Riemann surface of genus G, i.e. X is not conformal to Y. There's no biholomorphism. So a conformal map is one that preserves angles. It sends, so maybe here is X. It has some complex structure on it. Here is Y. I've drawn some genus 3 picture. And there's no map, for instance, that takes little infinitesimal circles. Maybe draw some little infinitesimal circles here to little infinitesimal circles here. I can't do that. There is no such map like that. But what I might be able to do, I might be able to take little circles. Maybe I can take little circles here and make them into little ellipses here, infinitesimal ellipses here. So this might exist, and in fact it does. So these are called quasi-conformal maps. They don't preserve angle, but they only distort angle a little bit. Or they distort sort of eccentricity of what's called an ellipse field, or I don't want to get into too much technical detail, but you can ask, so the natural notion of distance, what's called the Teichmuller distance between X and Y, is 1/2 log, I'll call it K of XY, where K of XY is the minimal quasi-conformal dilatation of a map between X and Y, of a QC map from X to Y. So the dilatation is in some sense a measure of how much your ellipses get distorted, and it's equal to 1 if your map is actually conformal. And so if you take log of it, you get 0, so then they're actually the same. And the question is, how do you do this? How do you actually get from X to Y? And of course, there's also this, there's kind of there's the X and Y also have kind of hyperbolic representatives. You could say, you give me a hyperbolic surface, you give me a hyperbolic surface. What's the kind of the best way in terms of distorting the complex structure the least to get from X to Y? And the answer is that you have to to do this, you actually have to understand flat geometry. So it turns out, and this is a paraphrase of a theorem of Teichmuller, is that there exists kind of a flat geometry on X. So there is some way of putting a flat geometry on X, of putting some honest-to-goodness flat geometry, maybe with some we'll have to have some singular points, such that by applying the map e to the t 0, 0, e to the minus t to this flat geometry. So thinking of this thing as maybe some polygon with some sides identified, and then just literally hitting it with this map, I'll get some now, this will stretch the horizontal and contract the vertical. So my drawing is not going to be very good because I'm also rushing at the end of the talk, but you get some kind of longer, sort of thinner version of this thing. It's going to get longer wherever it is. This isn't a perfect picture, my apologies, but I think you understand what I'm trying to do. And this will be my new Y here, which will have some sort of horizontal and vertical lines. The horizontals will have gotten longer, the verticals will have gotten shorter. And this map here will be that best quasi-conformal map that I talked about. It will take these lines, these vertical and horizontal lines, to these vertical and horizontal lines on Y. So you start with X and Y. There is this polygonal picture that allows you to just apply this linear map, e to the t0 through e to the minus t. This is called the Teichmuller map. And this associated trajectory, you apply it precisely with t is equal to, in this case, you want to apply it with t is equal to sort of 2 log k of xy. So you kind of just apply k of xy, t over 2, t over 2. And then you'll get exactly, you'll stretch in one direction, you'll contract in the other. And this will give you kind of the most efficient way of changing one surface into the other. And this comes more generally, there is a GL2R action on the space of these flat structures. You've probably heard a lot about this action. And the point is, these orbits correspond to what are called, this is a word you may not have heard, called Teichmuller disks. These are isometrically immersed copies of the hyperbolic plane into this moduli space of genus G Riemann surfaces. So the studying these flat structures allows you to understand really interesting submanifolds of the moduli space of Riemann surfaces, kind of really natural Hi, I think I disappeared for a moment. Am I back? Hello?
I think you your one screen.
I think I disappeared.
No. I think one of your screen has been frozen.
What was? Okay. What was the last thing you heard me say?
Yeah. Hello.
Oh, I was going to ask, what was the last thing you heard me say?
This is about the screen. The screen is not moving. This is the last thing I see.
Okay,
about the orbits of the.
Okay, that's fine. Okay, that's all. That's all I've written. I haven't written anything else.
Yeah.
And so let me just conclude by saying, is that bits of this action give you really interesting submanifolds of the moduli space of surfaces, and that's why we care about this, and that's why we want to study this. So this is only the start of a very long and really beautiful story, where there are many names to mention here, some of whom are in this room, but maybe some of the big names to really mention are Eskin and Mazer and Mirzakhani and Bill Veach, John Smiley. There's a tremendous amount of interesting work to understand this action of this group and understand how it plays with these moduli spaces of surface. So I think that's probably a good place for me to stop. What I wanted to do with these two lectures is just to give you a flavor of these how to build spaces of surfaces. The second lecture, I understand, was quite sketchy. It didn't have a lot of technical details, but I hope it motivates you to ask me some questions, or to be in touch with me, or to talk to Professor Tiwari or Professor Gonkopadhyay about these kinds of problems, because there's a tremendous amount of interesting research happening, certainly across the world, but also in India, about moduli spaces of surfaces. And you guys have some great people here to learn from. Hope this motivates you to go and talk to them and learn more about this beautiful subject. So I think this is a good place for me to stop.
Oh, thank you very much. Thank you very much, Professor Athreya. So any question or comment? Any question from any participant? So
Jaydev, I have a question.
Yeah.
Go for it, please.
Yeah. So you have the moduli space of hyperbolic structures. or the Teichmüller space that you can classify by
Yeah.
Fenchel-Nielsen coordinates. So is there any analog of Fenchel-Nielsen? Hello, am I audible? Yeah. So is there any analog of
I can hear you just fine.
Fenchel-Nielsen? Yeah. Is there any analog of the Fenchel-Nielsen for the moduli space of flat structures on a surface?
Yes. So in some sense, that very natural coordinates on the space of flat structures are, I hinted at them in this talk by saying you just take these side lengths and you, or these vectors in R2 that determine the sides, and you just use that as coordinates. So these are, well, that's what's called period coordinates on the space of flat surfaces. And in some sense, so there's something, in fact, that you would like that I didn't really mention, but the Fenchel-Nielsen coordinates you can think of as coming from, a hyperbolic structure is a representation of the fundamental group into PSL2R, right? And then the Fenchel-Nielsen coordinates, or it's up to conjugation. And then the Fenchel-Nielsen coordinates are just the traces, right? Or logs of traces. For a flat surface, you have a representation into the group of translations, right? Of the fundamental group into the group of translations, which is just C. But of course, that factors through the abelianization of the fundamental group, which is homology. And so you fix a basis for homology, and you look at those representations. You look at the images of the representation. Those are just a bunch of vectors in C. So in some sense, this is the natural analog of Fenchel-Nielsen. And just like with Fenchel-Nielsen, if you change the Banks decomposition you pick, you get new coordinates. And here, if you change the basis of homology, you would get new coordinates.
Okay, so
Any other comments?
So
or
I was
questions?
disconnected, but anyway, I got what you were saying, and it was a great talk, by the way. I mean, it was fantastic.
Thank you. Thank you.
No, really, it's starting from just basic triangles, and just in 2 talks, you have completed almost semester teaching.
Yes, and certainly, I don't claim to have given any of the details, but what I hope is that this motivates the students to look up the details themselves and try and work through the details themselves. So I'll be happy, again, like last time, to send the notes that I sent, and then I'm sure, well, they have wonderful teachers like yourself, and here, so they have many people they can talk to.
So Jayadev, though I am sort of, I should not say it here, but anyway, since we are meeting, so there is this CIMPA school that is going to happen next year. Okay.
Right.
So if you are able to turn up during that time, it would be great. I mean, if you can give a course there also, I mean, maybe an expanded version of this.
So
talks.
let me look at my timings. I always love to come and visit you and to talk. And so what time of the year it is and so on. But I would be very excited to come and spend some time and interact with students and to
can you communicate with Jayadev to invite him during that time? And
Sure. Why not? It's 12 to 22 December next year.
Okay. That seems potentially feasible, and I would be excited to potentially participate. That'll be in Varanasi again next year, right?
Not only during your course. I mean, you can come for the whole duration in Kashi, and you can stay there.
And I see. I'm seeing, but also, I mean, I'm sure you guys already know about this, but this is I'm seeing many. It looks like there's already so many wonderful and exciting courses planned. With George and Atanas and Shubhajoy, and you guys have really organized an amazing meeting. I would be very excited, perhaps, to spend some time.
Okay.
But those are all tentative. We really do not know what will be the shape of the program. Because I think some of these courses will be cancelled. I'm sure. Not everybody.
Sure.
because they planned it, I think, around 2 years back. I mean, when
Right.
everything was normal.
Yeah.
All
Yeah.
right.
Right.
But now things have changed and everything is going to be changed. Yeah.
Yeah.
But in any case, you are invited, and I hope that we will meet there in person.
That
Yeah.
would
Yeah.
be
If
Sure.
not,
amazing.
Yeah.
if not at Aisar Mohali this time.
Absolutely, absolutely. So I'll
Yeah.
keep you posted, and also I just wanted to tell of course I'm in touch with all of you, but for the students, please feel free to reach out to me with questions. I've put my email address there,
Yeah.
and I'm always happy to interact with students and with colleagues. So please don't hesitate to send me an email. If you don't hear from me after sending me an email, don't hesitate to reach out again. Unfortunately, the spam filters on the University of Washington email have been a little bit overactive.
Yeah.
So if you don't hear from me there, you can also try and reach me at my personal email, which is that one.
Yeah.
Okay. So for the students, I just like to mention here that Jayadev is very much active in visualizing mathematical objects as well.
Yeah.
And he is one of the pioneer of a renovated geometry lab in the United States.
Yeah.
All right. So they experiment on several problems and draw beautiful pictures, mostly for research, but also for outreach. And I think some of you also do some 3D printing, right? I mean,
Yes,
that,
yes,
yeah.
yes, yes.
That is
The lab
one
definitely.
tool. Yeah, yeah. That is one tool that we have not able to start yet at India. I mean, it will be great if we can start, that sort of lab here. Yeah.
Absolutely. So there's some really interesting stuff, and yeah, for sure, I would be very happy to talk about visualization and animation and some of the other ideas that happen as well.
Yeah, yeah. Yeah, so if you happen to, I mean, yeah, let's see. I mean, we'll plan it
We'll
because
talk. We'll
yeah,
talk for sure.
yeah,
It's hard to plan anything right now, but
yeah,
we'll
exactly.
we'll definitely be in touch and we'll talk soon.
Yeah, yeah, absolutely. It was great.
Thank you guys. It was
Oh,
wonderful to
thank you.
talk to you.
Thank you. Thank you. Thank you, Professor Jayadev. Thank you. Thank you. Thank you. Yeah. Yeah. Okay. Yeah.
Bye bye.
Bye. Take care.
Okay. Bye.
Okay,
Okay, so
Venkatesh.
Krishnendu, so thank you
Yeah.
very much for organizing this
Welcome.
pre-CIMPA school and for your idea of organizing this pre-CIMPA school, and maybe we'll have before CIMPA we may have some more possibly at least one more
Yeah.
such.
Maybe you can stop the recording at the moment.
I think yeah.